In this video, we will continue our look at dehydration reactions to prepare alkenes. In earlier videos, we saw some examples and then we saw a detailed mechanism. So now we're going to make sure that mechanism is consistent with some of the other examples we saw. In an earlier video, we saw that cyclohexanol can be treated with phosphoric acid to give cyclohexene. If we think about the reaction mechanism, the alcohol can grab a proton, which gives us the protonated alcohol. Then water can leave, giving us a secondary carbocation. Keep in mind, this carbon was originally connected to the OH and one hydrogen, so this hydrogen is still here, but now that carbon only has the 3 bonds, this carbon has a positive charge. Let's put in a little more detail. Keep in mind that the carbons adjacent to the carbocation both have 2 hydrogens connected. Now remember where the alcohol is and now where the carbocation is, this is called our alpha position. And so this is a beta position and this is a beta position. These beta positions are equivalent to each other. So in the third step, when we have water acting as a base, it can grab off one of the hydrogens from the beta position, allowing these electrons to fold in here to form this double bond. And so we are again looking at an E1 mechanism, which proceeds through the formation of a secondary carbocation. Please keep in mind, dehydration is a beta elimination. So when we lose water from one carbon, we have to lose a hydrogen from the adjacent carbon. It's a common misstep that students show this hydrogen getting removed, but then that would put a lone pair on the carbon and the carbon would only have 2 bonds. That is not a stable species. Or students may show water grabbing off this proton, having these electrons go here to form the double bond. But when we can see these hydrogens, we know that we can't form a double bond here because that would give us 5 bonds to carbon. So although it's really convenient to use the skeletal structures as a type of shorthand, don't forget to include at least a few more details so that you're not making mistakes as you're working through the mechanism. We also saw in an earlier video that ethanol could be treated with sulfuric acid and heat, and that would result in the formation of ethylene. So as we think about the reaction mechanism, if this behaves the same as T-butyl alcohol and cyclohexanol, we're going to start out with the alcohol acting as a base and grabbing a proton from sulfuric acid. That will give us the protonated alcohol as an intermediate. Now, if this is exactly the same as the tertiary and secondary alcohols, then the next step would be water leaving, and that would give us this, which is a primary carbocation. Now we know that primary carbocations are really, really high energy, so this is not going to happen. We are not going to generate a primary carbocation. Instead, let's rewrite this in a little more detail. So here are my 3 hydrogens and my 2 hydrogens, and we've got our protonated alcohol. This has the positive charge on the oxygen. So unlike what we saw in the case of a tertiary or a secondary alcohol, with a primary alcohol, water is instead going to act as a base before the leaving group leaves. So once again, keep in mind, this is our alpha position, this is our beta position. So water can grab off one of these protons, allowing these electrons to fold in here to form the double bond, pushing away water as the leaving group. That will give us the alkene plus water plus H3O plus. So even in the case of the E1 mechanism, where we had a molecule of water acting as a base to grab off the beta proton, it wasn't necessarily the same molecule of water that just came off. So even though we have concentrated sulfuric acid, we still have water molecules present. So we will have another water molecule that can grab off a proton even while this water molecule is still connected. So in the case of a primary alcohol, this will undergo elimination by the E2 mechanism. Elimination bimolecular. Elimination because you end up with an alkene and water was lost. Bimolecular because this must be the rate determining step, and there are 2 molecules involved in the transition state of the rate determining step. So if we think about an energy diagram for this reaction, then this is our starting material where we have our alcohol, and then this would be our first step leading to our protonated alcohol. And then this is going to be our second step leading to our product. Again, I'm not trying to show the relative energy of the product compared to the starting material or the intermediates, but we know that proton transfer to and from oxygen is fast, and so this has to be a small activation energy, and this one then must be a relatively large activation energy. So this is the activation energy for step 2, which is the rate determining step. So E2 mechanism for primary alcohols. Now, to make sure the mechanism is consistent with the experimental results, let's look at another example and consider the selectivity, and let's see whether the selectivity is consistent with the proposed mechanism. So if we rewrite this starting material with a little more detail, so these are, here is our OH, now keep in mind, because this is our alpha position, this is a beta position, and this is another beta position. And those beta positions are not equivalent to each other. In the first step of the reaction, the alcohol will grab a proton, and that is going to give us, now I'm going to switch colors. So we have our protonated alcohol. And next, when water leaves, we are going to get this carbocation. Now, if water grabs off a proton from our red group, then these electrons will fold in here to form the double bond, and that is going to give us the first product. On the other hand, if water grabs off a proton from the blue group, these electrons will fold in here, and that gives us the alkene between carbons 2 and 3. So keep in mind, this will still give a mixture of cis and trans. So overall, the mechanism still works, and looking at this intermediate, we can see how the mixture of products is formed, at least between the 1-butene and the 2-butene. Because we have 2 different beta positions, either hydrogen could get removed. Now, let's think about this on an energy diagram. So here we have the energy of our starting material, and then this is the energy of our protonated alcohol. So this is our first intermediate. That's what our first step is going to look like. Now this is the energy of our carbocation. And considering the reaction pathway, this molecule is going to pass through a transition state until it gets to this intermediate. Because this is the formation of a carbocation, we know that this has a very high activation energy, and this is going to be our rate determining step. So the high energy intermediate and the high energy transition state leading to that intermediate is common for all three products. So the difference comes in after this rate determining step. Now let's think about our products in terms of their relative energies. We talked about this earlier, that a monosubstituted alkene is less stable than a disubstituted alkene. So let's say this represents the energy of our red product. We also saw that cis is less stable than trans. So maybe this is the energy of our cis product, and then this will be the energy of our trans product. Now let's think about the reaction pathway that gets us to those products. From our carbocation, this is going to pass through a transition state, and maybe that transition state is up here, leading to the formation of this product. Now I'm just going to extend this out. This is the energy of our carbocation intermediate. And if we look at the blue pathway, now maybe the transition state for the blue pathway is a little bit lower in energy than the red transition state. And so this reaction pathway is going to look like this, leading to our cis product. And then the green pathway, maybe that transition state is also just a little bit lower than the blue. So our reaction pathway is going to look like this, leading to our trans product. So this would be the activation energy for the last step leading to the red product. This is the activation energy for the last step leading to the blue product. And this is the activation energy for the last step leading to the green product. Now, keep in mind, Hammond's postulate tells us that states that are similar in energy are similar in structure, or states that are similar in structure would be similar in energy. So because this energy is much higher and this energy is much lower, then our maximum is going to be closer in structure, closer in energy to our carbocation. So all of these transition states are going to be very similar to the carbocation. They're similar in energy, they will be similar in structure. However, similar is not exactly the same. The red transition state has a little bit of this double bond character. The blue transition state has a little bit of this double bond character, and the green transition state has a little bit of this alkene character. And so that little bit of trans disubstituted alkene character makes this transition state a little bit lower than this one, which has the cis disubstituted alkene character, and this one is a little bit lower than this one, which has the monosubstituted alkene character. So technically, we do not get this as our major product because it's the most stable product. Instead, we get this as our major product because the transition state leading to it is lower in energy than the other transition states. So once we get to this common intermediate, the carbocation, there are 3 different pathways it can follow, and going through the green pathway is going to be easiest and fastest. And so most of the molecules are going to react quickly through the green pathway, And some of them will go through the blue pathway, and even fewer will go through the red pathway, which will lead to this product ratio. In our last example, we saw that if this secondary alcohol is treated with phosphoric acid and heat, we get a mixture of products. We get this product in about 3% yield. We get this product in 64% yield, and we get this product in 33% yield. Now, what you should notice is that these two products have a different carbon skeleton compared to what we started with. And so we know that this reaction, or we propose that this reaction, proceeds through a carbocation intermediate. The carbocation intermediate is consistent then with the possibility of a carbocation rearrangement, which would lead to a different carbon skeleton. So let's think about the mechanism. So step one, our alcohol is going to grab off a proton from phosphoric acid, and we are going to get this protonated alcohol. In step two, water can leave, and that will give us this carbocation. So keep in mind, we originally had one hydrogen here connected to this carbon as well as the alcohol. So when water leaves, we still have one hydrogen present. Now, this carbon is our alpha position. Here's a beta, and here is a beta. The beta on the left, there are no hydrogens that can be abstracted. So in the third step, water has to grab off one of these protons, allowing these electrons to fold in here, which will give us this product. And this one corresponds to our first product. But let's come back and take a look at this carbocation intermediate. So we know that this is a secondary carbocation, and we need to consider the possibility of carbocation rearrangement if a secondary carbocation can rearrange to a more stable tertiary carbocation. I'm going to redraw this. So here we have a CH3, here's our CH, this is our carbocation, here's a CH3, and here is our other CH3. So right now we have a secondary carbocation. If the blue methyl group with its pair of electrons decides to take these electrons and share them with this carbon, then we are going to get this intermediate. And now this carbon is the carbocation. So now this carbon is the alpha position, which means this is a beta position and this is a beta position. So if water grabs off a proton from this position, then that leads to the formation of this alkene. Or if water grabs off this proton, that leads to the formation of this alkene. And in this way, we have accounted for all three of the observed products. So keep in mind that even though a mechanism can never be proven, we want to be sure that a proposed mechanism is consistent with all of the experimental results. And so for T-butyl alcohol or cyclohexanol, an E1 mechanism makes sense to lead to the alkene products. For a primary alcohol, an E2 mechanism makes sense to lead to the formation of the alkene product. In the case of a secondary alcohol with unsymmetric beta positions or with non-equivalent beta positions, then the mechanism can account for the different product ratio. And finally, in the case of an alcohol that led to a mixture of products with a rearranged carbon skeleton, then the E1 mechanism with carbocation rearrangement is also consistent. So finally, let's summarize the preparation of alkenes from alcohols. So this is a dehydration reaction, which proceeds through the loss of water. The reaction conditions that you need to recognize would be a strong acid such as sulfuric acid or phosphoric acid, and heat. Tertiary and secondary alcohols will undergo the E1 mechanism, which proceeds through a carbocation, and primary alcohols will proceed through the E2 mechanism, which has no carbocation. Methanol cannot undergo a dehydration because it can't form an alkene with only one carbon. So keep in mind that the reaction could be, depending on the structure of the starting material, the reaction could be regioselective, and in this case, the preference is for the more substituted alkene. The reaction may be stereoselective, where trans is preferred over cis. And there is a possibility of carbocation rearrangement. So the amount of carbocation rearrangement can be difficult to predict. I don't need you to try to calculate or estimate how much is going to happen. I want you to be on the lookout when it could happen, or I want you to be able to explain experimental observations when a carbocation rearrangement did happen. So this wraps up our look at dehydration reactions to form alkenes.